Every year, over 1 billion new tires appear in the world, and just as many used ones end up in landfills. Imagine in the United States alone, over 250 million tires are recycled annually, saving the planet from mountains of trash. But where do these black rings, which have served their thousands of miles, disappear to? They don't just vanish, they go through fire, steel, and the grindstones of machines to be born a second time. And the most exciting part, we don't even realize that we walk on their second life every day. Stay until the end, because there, I will reveal a secret that will forever change your perception of an ordinary tire. So today, we're heading to a cemetery. A car tire cemetery. Acres of land, piled high with mountains of black rubber rings. These are the silent veterans of the roads, who have driven their thousands of miles and now lie here, seemingly unwanted by anyone. But this is not the end of their story. It's just the beginning of their amazing reincarnation. We will trace how these worn, dirty pieces of rubber go through a series of brutal yet high-tech trials to be reborn as the soft, resilient heart of a modern sports stadium. This is a story of how the roar of the road turns into the quiet whisper under the feet of athletes. Americans have learned to give a second life to the vast majority of tires. The recycling rate for old tires in the United States is now over 85%. This is one of the highest rates for any consumer product. This means that over 250 million tires annually avoid the landfill and are sent for rebirth. Some of them are burned as highly efficient fuel. Some are used in civil engineering, but a significant and ever-growing number are turned into that very rubber crumb. In this tire cemetery works a machine that looks like a steel Tyrannosaurus. This is an industrial shredder. A huge loader grabs a whole handful of old tires and throws them into the steel maw of this machine. Inside, 2 massive shafts with thick, sharp hooks rotate with a deafening screech. They grab the tires with relentless force and with an incredible crack, tear them into pieces. There is no delicacy here. The shredder's task is simply to break the integrity of the tire, turning it into coarse pieces the size of a palm. At this moment, the first important release occurs. Inside each tire is a steel cord, a strong frame of steel wire. During the tearing, this cord is released, turning into a shiny web of steel threads, mixed with rubber pieces. This chaotic mixture of rubber and steel moves further along the conveyor. And here, an industrial, powerful, huge magnet comes into play, rotating above the stream of shredded material. It, like a refrigerator magnet, but 1,000,000 times stronger, pulls all the steel threads from the rubber mass. With a screech and a clang, the steel cord sticks to the magnet and is dropped into a separate container. This steel will then be sent for remelting, and our cleaned rubber continues its journey. But it is still too large and coarse. The next stop is the granulator. This is something like an enraged coffee grinder the size of a car. Inside, sharp knives rotate at a huge speed, grinding the large pieces into a finer fraction, the size of a fingernail. During this process, another component of the tire is released, the textile cord. These are nylon or polyester fibers that gave the tire additional strength. These light, fluffy fibers need to be removed. For this, the rubber granules pass through a system of vibrating screens and air separators. Powerful streams of air literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now, we have a clean, but still quite large material. To become a stadium covering, it needs to be turned into crumb. For this, the granules are sent for final grinding, often in so-called cracker mills. These are 2 massive grooved steel rollers that rotate towards each other at different speeds. The rubber granules, falling between them, are not so much cut as they are torn and ground into the smallest particles. As a result of this process, we finally get what it was all for: rubber crumb. This is a uniform, free-flowing mass, similar to black caviar or coarse sand, where the size of each particle is only a few millimeters. This crumb is carefully sifted to guarantee perfect size uniformity and packed into huge bags, weighing a ton each. Its journey from a dirty tire to a clean, high-tech raw material is complete. And now let's move to the place where this black crumb will find its true calling, to the construction of a new stadium. Workers roll out huge rolls of artificial turf on a perfectly leveled gravel base. This isn't just a green carpet. It's a base with long, soft polyethylene blades of grass sticking up. But for now, they look sad and limp, pressed to the base. For them to stand up and look like real grass, they need support. And here, a special machine, similar to a large fertilizer spreader, drives onto the field. A process called infilling begins. First, the machine evenly spreads a layer of fine, rounded quartz sand over the entire field. It is heavy and settles at the very base of the carpet, acting as a ballast so the turf doesn't shift, and helping to stabilize the blades of grass. And following the sand, our main hero is poured onto the field black rubber crumb. The machine just as evenly distributes it over the entire surface. And this is where the main transformation happens. This crumb fills the space between the blades of grass, making them stand vertically, like real grass. Secondly, and most importantly, it creates a cushioning layer. When an athlete runs, jumps, or falls, this layer of billions of tiny, resilient rubber particles compresses, absorbing the energy of the impact. It's like running on a billion tiny trampolines. This sharply reduces the load on the athlete's joints and makes falls much safer. The final touch is combing the field. A special machine with a huge brush drives over the turf, thoroughly mixing the sand and rubber crumb and combing them deep to the very base, making each blade of grass stand perfectly straight. And so, when the work is done, before us is a perfectly green, resilient, and safe field. And none of the players running on it may even guess that under their feet, between the bright green blades of grass, lie millions of particles of old car tires, which have completed their epic journey from the roar of the highway to the quiet, resilient covering of a sports arena, having received a second, much nobler life. To create one standard field for American football or soccer, you need an average of 20,000 to 40,000 old passenger car tires. Just think about it. A single field completely eats a whole mountain of rubber trash. And how many such fields are there in the country? There are now over 13,000 fields, with artificial turf in the USA in schools, colleges, parks, and professional arenas. And this number is growing every year. And now for some simple math. If we take even the minimum figure of 20,000 tires per field, it turns out that in the coverings for sports fields across the country, over 260 million old tires have found their new home. This is almost a year's supply of all the rubber scrap that the country generates. Natural turf is a very capricious thing. It needs to be constantly mowed, watered, fertilized, and given rest. On average, a natural field can withstand no more than 20 hours of play per week. And a field with artificial turf? It can work 24 hours a day, 7 days a week, in rain and in heat. And now about water. One field with artificial turf can save from 500,000 to 1 million gallons of water every year. This is the amount of water an average family uses in several years. Add to this the savings on fertilizers, pesticides, and the work of lawnmowers, and the benefit becomes obvious. So the next time you see a bright green field, know that it's not just a place to play. It's a monument to human ingenuity that solves the problem of trash, makes sports safer, and saves precious natural resources, one old tread at a time. Imagine thousands of glass threads, thin as a hair, combined into a single river, are transformed into a material that is already challenging steel. This isn't science fiction, but modern production of fiberglass rebar. Every year, the world spends billions fighting rust, repairing bridges and parking garages destroyed by corrosion. But there is a solution, a composite that is twice as strong as steel, 4 times lighter, and doesn't even know what rust is. The market for this material is growing by 12% annually, and today you will see how a building material of the future is born from hundreds of bobbins and a barrel of resin. It all begins at one end of a huge workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall, several yards high, hundreds, and sometimes thousands, of huge bobbins are installed in neat rows. On each of them is wound the thinnest glass thread, or roving. This isn't the glass that windows are made of. This is a special fiberglass, which is produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. They will be our skeleton, our internal army, which will give the rod its insane strength. From each of these hundreds of bobbins stretches its own separate thread, and they all gather into one thick, fluffy bundle. It's like thousands of streams merging into one large river. This dry white bundle is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Each of the thousands of threads must be tensioned with the same force. If one thread sags and another is over-tensioned, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment baptism in resin. The dry glass bundle is slowly immersed in a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat, that will grow on the glass skeleton. This is a complex chemical cocktail. The base is usually polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will start a chemical reaction and force the liquid to turn into a solid plastic. Also, various additives can be added here. Pigments to give color, ultraviolet inhibitors so that the rebar is not afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to soak every, even the tiniest fiber. The bundle must be completely submerged in this resin so that not a single dry spot remains. The soaked, heavy from sticky resin bundle comes out of the bath and heads to the point of its birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round, polished hole, the diameter of which exactly corresponds to the diameter of the future rod. The die is heated to a certain temperature. When the wet bundle is drawn into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass together, forming a perfectly round rod. Third, the heat from the die starts the initial stage of the chemical reaction of hardening, or polymerization. The resin begins to turn from a liquid into a gel. At the exit of the die, we already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special bundle of the same fiberglass is wound onto it. A thin, resin-soaked thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled on the sticky surface, which sticks firmly to the resin. Now our rebar has not only strength, but also teeth with which it will hold onto concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization furnace. This is a long chamber that can stretch for tens of feet, inside which a high temperature is maintained, usually 400 Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively connect with each other, forming a strong, rigid, three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material, which firmly binds millions of glass fibers into a single monolith. It's like baking a pie. While the rod slowly moves through this hot tunnel, it acquires its final, stone-like hardness. But what pulls it through this whole long path, from the bobbins to the furnace? At the end of the line stands a special pulling device, which gave the whole process its name. Usually, these are two caterpillar mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads, and at a constant, precisely calibrated speed, pull it towards themselves. It is they who create the force that pulls the fiberglass through the resin bath, through the forming die, and through the furnace. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor appears an endless, perfectly even, hard and hot fiberglass rod. The final chord is cutting. Across the line is an automatic saw. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward movement, and with a sharp whiz, cuts off a piece of standard length from the endless ribbon, for example, 20 or 40 feet. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And so, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and furnaces, have turned into a light but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungles. The fiberglass rebar market is not yet a giant like the steel market, but it is the coolest and most daring newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are simply insane. It is expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now about the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sounds boring? Now imagine it in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it is limited by weight. Or, for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can calmly carry whole coils or bundles of fiberglass rods, whereas a crane is needed to move steel. This is a colossal saving on logistics and labor. Second is strength, and here fiberglass simply enters the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing an ordinary rope with a climbing rope. At a smaller thickness, it withstands much greater loads. But the main trump card, the real superpower of fiberglass, is its war with rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load, it's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. Rust increases in volume and literally tears the concrete from the inside. Annually, the United States spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years. And a structure with fiberglass rebar is calmly designed for more than 100 years. Every year, over 9 million tons of copper scrap are recycled worldwide. That's enough to build 1,800 statues of liberty. But where do old cables, transformers, and copper wires go after disposal? What do they do with them in the heart of factories where temperatures exceed 2,000 degrees Fahrenheit? And why can recycling 1 pound of copper save as much energy as a whole house needs? If you watch until the end, you'll learn a secret you've never heard before. So, in what city did you last see a copper factory? Write it in the comments. It's interesting to check the geography. It all starts at the huge warehouses of recycling plants. Thousands of pounds of various copper scrap flock here. Thick power cables from industrial sites lie next to thin wires from household appliances. Old transformers are neighbors with remnants of construction wiring. Each element has its own story, but they all share one thing. They are ready for a new life. The first stage of recycling is careful sorting. Experienced specialists separate the scrap by type and degree of contamination. Clean copper wire is separated from insulated cables. Thick industrial cables are separated from thin household wires. This is a critically important step, as different types of scrap require different approaches to recycling. The next stage is mechanical cleaning, a true art of modern technology. Powerful shredding machines cut the cables into fragments 2 or 3 inches long. Special separators use the difference in material density, as copper is heavier than plastic and rubber, making it easy to separate. Vibrating tables and air currents finally clean the copper fragments of insulation remnants. The output is relatively clean copper pieces, but this is just the beginning. The real magic begins in the melting shop. Huge induction furnaces heat the copper to a temperature of over 1,984 degrees Fahrenheit, the melting point of copper. The metal fragments gradually turn into a red-hot, almost golden liquid. This sight is always impressive. Hard, cold pieces of metal become a living, pulsating mass. But temperature is just a tool. The main action happens at the molecular level. During melting, impurities behave differently. Some float to the surface as slag, others dissolve. Master metallurgists carefully control the process, skimming off the slag and adding special substances called fluxes, which help remove unwanted elements. The first refining is complete, but this is not the end. The molten copper is poured into special baths for electrolytic purification. This is the most precise stage of the entire process. An electric current of several thousand volts is passed through the melt. Under its influence, residual impurities, iron, nickel, zinc, lead, migrate to the electrodes and are removed from the melt. Electrolysis lasts for several hours. The temperature is strictly controlled between 2,100 and 2,200 degrees Fahrenheit, and the current strength is regulated with an accuracy of tenths of an ampere. Laboratory analyses are conducted every 30 minutes. Chemists check the metal's composition, tracking how the amount of impurities decreases. Gradually, the purity of the copper increases: 95%, 97%, 98%, 99%. And finally, the coveted mark of 99.9% is reached. The purified copper is ready for forming. The molten metal is poured into special molds, ingot molds. The molds are preheated to a temperature of about 1,800 degrees Fahrenheit to avoid thermal shock. Slow, controlled cooling allows the copper to crystallize with the correct structure. Perfectly uniform ingots weighing from 50 to 100 pounds or cylindrical billets 6 or 8 inches in diameter are formed. These billets are the basis for future cables. They go to the wire drawing shop where the next transformation takes place. A wire drawing machine is a series of successively arranged dies, openings of different diameters. The billet passes through the first opening, about 3 inches in diameter, then through a smaller one of 2 inches, then 1.5 inches. With each pass, the diameter decreases and the length increases. The drawing process requires enormous effort. Powerful electric motors with up to 500 horsepower pull the copper through the dies with a force of tens of tons. The metal deforms but does not break because copper is plastic and can withstand such a load. Gradually, the thick billet turns into a thin, flexible wire with a diameter from 1/2 inch to even thinner. Each stage of drawing is strictly controlled. The diameter is measured by laser devices. The feed speed can reach 100 feet per minute and is automatically regulated. If defects appear, such as scratches, irregularities, or cracks, the process is stopped for correction. The finished wire undergoes a final quality control. Not only the geometry is checked, but also the electrical properties. The resistance must not exceed a certain value per 1,000 feet of length. Conductivity, mechanical tensile strength. All parameters must comply with strict American Society for Testing and Materials standards. After all, this wire will become the basis for cables that will transmit electricity to homes, offices, and factories. The final stage is the manufacturing of the finished cable. Copper wires are covered with insulation up to 1/10 of an inch thick, polyethylene, polyvinyl chloride, or other modern materials. Depending on the purpose, the wires can be twisted into the required configuration. Power cables for 120 or 240 volts, information cables of category 5 or 6, special purpose cables, each has its unique design. Packaging the finished product is the final touch. Cables are neatly wound onto spools, 3 or 4 feet in diameter, or placed in boxes of standard sizes. Each unit is marked, indicating the length in feet, the cross-section in American wire gauge, and technical specifications. Underwriters' laboratory certificates confirm that the product meets all American safety standards. The result of this complex technological symphony is impressive. From scrap that seemed like useless junk, high-quality cable is born. It is ready to serve for 25 or 30 years, providing reliable transmission of electrical energy from residential buildings to large industrial complexes. But this is not just a technological process. It is a philosophy of sustainable development in action. Every ton of recycled copper is a ton that does not have to be mined from the Earth's depths. It means conserved natural resources, less environmental impact, and a cleaner environment for future generations. Recycling 1 ton of copper saves about 2.5 tons of ore. The cycle is complete, but it is endless. When, decades from now, this new cable becomes obsolete again, it will return here to begin a new journey of transformation. Copper is the metal of eternity, which can be recycled an infinite number of times without loss of quality. And in this lies its true value. The production figures are staggering. Over 9 million tons of copper scrap are recycled annually worldwide. This is equivalent to the weight of 1,800 statues of liberty. In America, the average family uses about 280 pounds of copper in their home, from electrical wiring to plumbing pipes. 1 million pounds of recycled copper saves enough energy to power 1,000 homes for a year. This is 85% less energy than is needed to mine new copper from ore. Recycling also reduces carbon dioxide emissions by 65% compared to primary production. The largest amount of copper scrap comes from the construction industry. That's 31%, from electronics, 21%, and from the automotive industry, 12%. 1 pound of copper wire can be drawn to a length sufficient to wrap around a football field 23 times. Modern factories can process up to 400 tons of copper scrap per day, producing wire with a total length of over 50,000 miles. Over the last decade, the price of copper scrap has increased by 180%, making its recycling extremely profitable. Today, recycling provides 40% of the world's copper needs, and this figure continues to grow. Every hour, over 3,000 miles of electrical cables are laid worldwide. But few people know that this involves gigantic metal spools, each one an engineering marvel weighing over 20 tons. Their diameter can reach 33 feet, and inside, up to 37 miles of wire capable of transmitting hundreds of thousands of volts. A half-inch error, and everything goes down the drain in losses. How are these steel giants created with precision down to 1/100th of an inch? And why can't any power transmission line exist without them? Watch, and you'll be amazed. This story begins with calculations. Before the first bolt touches the steel, a team of engineers dives into mathematical alchemy. Each spool for a high-voltage power transmission line is created for a specific type of cable, so there are no trifles here. Blueprints, models, and calculations come into play. It is necessary to consider the outer diameter of the cable, for example, 2 inches. Its weight, which can exceed 3 pounds per foot. Density, number of turns, winding angle, and even the insulation's coefficient of friction. On average, up to 6 miles of cable are wound onto one spool. That's almost 32,000 feet of heavy, multi-insulated wire that, under voltage, can carry hundreds of thousands of volts. An error of just half an inch in the spool's diameter, and the cable might start coiling incorrectly, shifting, compressing, overheating. In the worst case, it gets damaged even before installation. And that's tens of thousands of dollars in losses before even starting. Moreover, the core diameter of the spool can reach 5 or 6 feet, and the total diameter of the flanges up to 33 feet. The weight of the structure exceeds 40,000 pounds. That's like 2 large SUVs, screwed together and stood upright. And this entire mass has to rotate smoothly, without misalignment or vibrations. Are you impressed? Because I sure am. To avoid disasters, engineers add a coefficient of material expansion. As metal changes size when heated, consider transport weather conditions, and also the winding geometry, because even too steep a winding angle can damage the cable when it's unwound. When the drawings are approved, giant workshops come onto the scene, hangars the size of a football field. Here, metal flanges, cores, and frames appear. Most often, the spools are made of steel. It's steel that can withstand the weight of the cable and the loads during transport. For an average spool, more than 2 tons of steel are needed at the laying site. So, each giant spool for power transmission lines starts with cold metal, thick steel sheets that arrive at the factory as plates measuring 6 by 12 feet or more. Their thickness ranges from half an inch to 1 inch, and this steel is structural. Strong, tough, capable of withstanding high loads without cracking or deforming. First, the sheets are fed to plasma or laser cutting machines, which are programmed according to precise drawings. A giant plotter, emitting a hot beam, literally burns complex shapes into the metal. These machines operate with an accuracy of 1/100th of an inch. Such precision isn't for beauty's sake, it's critical. Because even the slightest error on one flange can cause the spool to lead the cable off-center during rotation. And that's a risk of misalignment, jamming, and failure during installation. The discs for the flanges are cut in pairs, identical rings 20 to 33 feet in diameter, with holes for connecting bolts. Technical slots and markings for future reinforcing elements are made on the surface right away. After cutting, they are processed by grinding machines. Burrs are removed, and they are prepared for welding. At the center of the future spool is the core, a large steel pipe that will serve as the drum for winding the cable. Usually, its diameter is from 5 to 8 feet, and its length up to 10 or 16 feet. The pipe is cut from thick wooled rolled stock and reinforced with stiffening ribs inside. These are thick steel strips that form a frame and prevent the pipe from sagging under the weight of the cable. After all the parts of the future spool are cut, the stage where every millimeter matters begins: welding and assembly. Here, metal geometry transitions from 2-dimensional to 3-dimensional. 2 giant flanges are attached to both sides of the core. A steel pipe that will hold tens of thousands of feet of heavy cable. The entire structure must withstand not only its own weight, but also dynamic loads during rotation and transport. Welding is done manually or automatically, depending on the size and complexity. Most often, submerged arc welding is used, which allows for creating dense, strong seams without voids. The joints are additionally ground, as any protrusion or unevenness can damage the cable during winding. Then, reinforcement. Stiffening ribs, which are thick steel plates placed inside the core and at the joints with the flanges, are added to the structure. They prevent deformation under pressure. To fix all the parts, bolts up to 1.5 inches in diameter are used, tightened with special hydraulic torque wrenches. One such bolt can withstand a load of tens of thousands of pounds. The finished spool is installed on a temporary axle and rotated. Engineers check the balance using a laser level, ensuring that during rotation, no part shifts even 1/4 inch. If the structure wobbles, it's ground, adjusted, and sometimes parts of the elements are reassembled. And only after this is the spool considered ready for the final stage: anti-corrosion treatment, painting, and testing. The finished spool has just been removed from the rotating stand after welding. It's still warm, smells of metal and ozone, and its surface is covered with dark gray spots. That's scale. It looks like a thin crust, similar to coal dust, and remains after the metal comes into contact with high temperature. Along with it, small remnants of oil, dust from grinding, handprints. Painting in this state is a waste of time. The coating won't stick, it will peel off in the first few months. So first, mechanical cleaning takes place. The workshop buzzes with tools. Workers with stiff brushes on grinding machines go over the joints, flanges, and stiffening ribs. They remove rough irregularities, clean the seams of residual slag. But this is not enough. Next, a sandblasting unit comes into play. A large chamber, or just a separate section in the workshop. The spool is brought inside on a special platform. Then, the roar of a compressor and a stream of fine abrasive starts hitting the steel surface under high pressure. Sometimes quartz sand, sometimes steel balls. It sounds like a storm of hail hitting tin. The surface changes before your eyes. Where there was just dark mottling, now there is an even, matte gray metal with a slight roughness. If you run your finger over it, you feel not smooth, but slightly velvety to the touch. This is exactly what's needed, because this micro-roughness significantly improves adhesion with the anti-corrosion primer. In chemistry, this is called the anchor profile effect. When the treatment is complete, the entire surface is blown with air, blowing out residual abrasive from corners and crevices. This is the perfect moment to apply an anti-corrosion primer, the first protective barrier between the metal and the environment. A worker in a mask and protective suit takes a sprayer with a thick gray liquid, a zinc-rich primer. With each press of the trigger, a thin, even mist comes out of the nozzle, settling on the surface. The zinc in the primer acts as a sacrificial metal. It is the first to react with moisture, saving the steel from corrosion. After a few minutes, the spool is already covered with a thin, almost invisible layer. It looks a little lighter, as if dusted. In a few hours, this primer will polymerize and form a chemically resistant film that is firmly bonded to the metal. It is this layer that takes the first hit from time, moisture, and temperatures. For export or harsh climatic zones, additional layers may be applied. Marine varnish, hydrophobic films, or even heat-resistant coatings that can withstand heating up to 300 degrees Fahrenheit. When the coating dries, the spool is carefully inspected. Under ultraviolet light, all microcracks, bubbles, or gaps in the layer are visible. If there are doubts, an electric spark test is performed. A special probe glides over the surface, and a spark jumps only where the insulation is compromised. This ensures that every inch of metal is reliably protected and will withstand years of operation in any conditions. Every year, over 300 million electric motors are manufactured worldwide, from miniature ones that spin coolers in laptops to giants that power trains, factory lines, and mine elevators. And each one of them is not just a coil of wires and iron, but a complex system of dozens of precisely calibrated parts. How is the heart of a machine born? Why is winding similar to weaving, and balancing to jewelry making? And how does one spark power a rotation that will last for thousands of hours? Let's take a look behind the scenes of one of the greatest technical processes, the creation of an electric motor. Inside every electric motor is a true mechanical electrical universe. The main components of a motor are the stator, rotor, shaft, bearings, housing, as well as a cooling system and terminal box. The stator is the stationary part, located in a circle inside the housing. It's what creates the magnetic field that makes the rotor spin. Inside the stator is a core made of layers of thin electrical steel, which reduces losses from eddy currents. In the slots of the core is a winding of copper wire, connected in a special way to create a rotating magnetic field. The rotor is the moving part inside the stator. It either has its own winding or is made in the form of a squirrel cage. Aluminum bars cast into a steel core, which form closed current loops. When the stator's magnetic field interacts with the rotor, it starts to rotate. The shaft is a rod that passes through the rotor and extends outside the housing. It's on this shaft that pulleys, impellers, reducers, or other drives are mounted. It transmits rotation to the mechanisms. The shaft must be precisely centered. Otherwise, the motor will vibrate and wear out quickly. Bearings, usually two, one at each end of the shaft. They ensure smooth rotation with minimal friction. For reliability, they are lubricated with special greases or are sealed. The housing protects the internal elements from dust, moisture, and mechanical damage. It often has fins for heat dissipation or even a fan. The material is cast aluminum or cast iron, depending on the power and purpose of the motor. The cooling system, most often it's simple air cooling, a fan on the shaft drives air flows through the housing. In large industrial motors, liquid cooling or external air circulation through special channels is used. The terminal box is on the outside of the housing. This is where the power cables are connected to the stator winding. Inside, contacts, clamping screws, and sometimes temperature sensors. In the depths of the factory, in a workshop that smells of varnish, metallic dust, and warm insulation, stands a giant stator. A stationary ring with slots around its circumference. This is its core, made of thin steel sheets, tightly pressed together. In each slot of this ring will lie copper wire, carefully laid, loop by loop, turn by turn, because whether the motor will rotate at all depends on this. Before starting the winding, the stator frame is thoroughly prepared. The slots are lined with special insulating liners, like nests for the wire. These are materials that withstand high temperatures, vibrations, and electrical loads. And only when they are sure that the insulation is perfect, the winding machine is started. The machine, resembling a giant spool that unwinds copper wire from a bobbin, wraps it around guides and lays it in the slots. Everything is automated, but under the supervision of a specialist. One sharp movement, and the wire could lay with a kink or snag the insulation. And that's a potential short circuit. For powerful or non-standard motors, winding is done by hand. A worker inserts the wire in a loop, pulls it through with a tool, presses it to the bottom of the slot, secures it, and tightens it. The work is similar to weaving, but with shiny copper and immense responsibility. Each coil, and there are dozens of them, must be identical, symmetrical, and correctly oriented. After the first layer of winding is completed, interphase insulation is laid, and then the second layer is placed. The wire forms closed loops, phases, which are then connected in a star or delta configuration, depending on the motor's setup. Then, the wires are secured with strings or plastic fasteners, the tension and geometry are checked, and if necessary, adjusted by hand. And finally, impregnation with varnish or epoxy resin, so that all this doesn't shift even a micron under vibration and temperature under load. If the stator is the skeleton, then the rotor is the muscle. It moves, rotates, creates torque. It's not visible when the motor is running, but it's what drives everything, from a fan to a train. At the core of the rotor is a steel shaft, long and powerful. Around it, the core is mounted, a set of thin electrical steel sheets stacked into a cylinder. The sheets have slots. These are for the conductors. This is where the most interesting part begins, creating the winding that will make the rotor come alive. One of the most common options is the squirrel cage. Aluminum or copper bars are inserted into the slots, and both ends are cast into rings, like a hoop around a cage. This creates a closed current loop. Such a design doesn't need to be connected directly. Current is induced inside automatically as soon as the motor starts. It's a simple, reliable, and mass-produced option for industry. But if the motor is more complex, more powerful, then classic windings are used. A worker manually lays copper wire in each slot, carefully tightening it, bending it at an angle. Here, symmetry, precise geometry of the turns, and perfect insulation are important. The wire must lie right, not touching the metal anywhere, not crossing over, not being too tight or too loose. A mistake, and the motor will overheat or fail. The rotor windings are then connected in a specific sequence: star, delta, or another type of connection. Everything is secured, insulated, and sometimes varnished. The insulated ends are led out to slip rings or brush assemblies, depending on the design. After this, the rotor is balanced, as it has to rotate at speeds of thousands of revolutions per minute. Any extra 100 grams on the edge, and everything will vibrate, hum, and heat up. The result? A compact, shiny cylinder with windings of copper wire or closed bars. It will be inserted into the stator, and the magic of converting electricity into motion will become possible. It all starts with checking dimensions and tolerances. The gap between the rotor and the stator, the so-called air gap, must be very small. If it's too narrow, friction will occur. If it's too wide, the magnetic field will be weak, and the motor will lose efficiency. The rotor is mounted inside the stator via bearing assemblies. Sometimes special guides or hydraulic presses are used for this. The rotor shaft must rotate perfectly straight, otherwise everything will vibrate or break down within a week. At the ends of the rotor shaft, sleeve or rolling bearings are installed. They allow the rotor to rotate without friction. The bearings are placed in so-called end shields, which are then attached to the motor housing. All surfaces are pre-lubricated with special greases to ensure durability. The ends of the stator and, if necessary, rotor windings are led out to the terminal box. Here they will be connected in the required circuit, star, delta, or another. In complex motors, temperature sensors are installed to detect overheating before a failure occurs. The motor is now assembled, stator and rotor in the housing, wires connected, bearings in place. But it's too early to start it. First, varnishing, drying, balancing, and testing. All like a ritual before the birth of a real machine's heart. In a spacious room with a specific smell of epoxy resin, the stator windings, and sometimes the rotor, are coated with electrical insulating varnish. This isn't just for dust protection. The varnish strengthens the structure, secures the wires so they don't vibrate at high speeds, and prevents moisture penetration. Application is either by dipping in a bath or by spraying. The motor is completely submerged in a tank of varnish, then removed and left to drain off the excess. Next is drying in a thermal chamber at a temperature of 250 to 300 degrees Fahrenheit. This stage resembles baking. The varnish polymerizes and forms a hard protective film. After varnishing, the most sensitive stage, the motor is installed on a balancing stand. The system is like a huge record player. The motor rotates at high speed, and sensors detect the slightest deviations. Even a few grams of excess mass on the rotor can cause vibration that will destroy the bearings, shorten the service life significantly, or even ruin the motor. To eliminate the imbalance, engineers drill microscopic holes in the heavier part of the rotor. removing excess metal. This is almost a jeweler's craft. The finished motor is sent to the test stand. Here it comes to life for the first time. It's connected to a power supply. Rotations, noise, heat, current consumption are recorded, and efficiency and power are measured. Everything is documented. The motor's passport contains dozens of parameters. If the motor passes all tests, it's packaged, a seal is applied, and an instruction manual is added. And very soon, this motor could be working on a conveyor, in an elevator, or in an electric train, wearing down metal and converting current into motion, without rest for tens of thousands of hours. Every year worldwide, over 200 million miles of steel wire are produced. That's enough to wrap around the Earth more than 8 times. But few people imagine how this silvery vein of strength is born, the one that holds up bridges, elevators, cranes, and even underwater cables. Its path is a trial by fire, acid, pressure, and time. How do you turn 10 tons of rough metal into a thin, shining thread capable of withstanding hundreds of tons of load? In this video, we're going to dive into the most secret workshops where steel becomes the muscle of civilization. And we guarantee you won't be able to tear yourself away. To create a steel cable capable of holding up a bridge hundreds of feet long, it all starts with the right alloy. Most often, it's carbon steel, with a carbon content of around 0.6%, which provides both strength and elasticity. Sometimes chromium, nickel, or molybdenum are added for corrosion resistance and increased load capacity, especially for cables that need to work outdoors for decades. The metal is delivered to the factory in the form of huge steel slabs, plates 10 by 2 by half a foot in size and weighing up to 10 tons. They are heated in furnaces to 2,200 degrees Fahrenheit until the steel becomes malleable, almost like rubber. Then these red-hot billets are passed through rolling mills, turning them into long, thin rods with a diameter of approximately 0.25 inches. These are called wire rods. These wire rods are then cooled under controlled conditions, either in air or in special baths, so that the metal structure is dense and the internal stress is uniform. Next, a short storage stage. The metal is weighed, checked for hardness, flexibility, and the presence of microcracks. Only after this is each coil sent to the main section, wire drawing, from which the future cables will be formed. After the steel wire rods have been cooled and checked for quality, they proceed to the wire drawing workshop. This process transforms the thick rods into thin but incredibly strong wire, which will become the foundation for bridge cables. Imagine a steel rod as thick as your finger, just off the billet. Its surface is rough, as if covered in a layer of sand or rust. This is scale, a hard and brittle crust that appears during hot rolling. To prevent it from interfering with further metal processing, it needs to be removed. To do this, the wire rod is first lowered into a bath of acid solution, usually sulfuric or hydrochloric acid. In this solution, the scale seems to flake off the metal, just like old paint peels off after being treated with solvent. Then the wire is rinsed with a large amount of water under pressure to wash away all traces of acid and dirt. To the touch after this, the metal becomes smooth and cool, like a freshly polished stone. But that's not enough. Next, the wire goes through degreasing. It's submerged in special alkaline solutions that remove any oils that might have gotten onto the surface. And only then is the clean, smooth wire, shiny and dry, ready for the next stage, drawing. Now, the wire needs to be pulled through a hole, smaller than the wire itself, to stretch it out and make it thinner. But a thick end simply won't fit through. So, it's first sharpened. This process is called pointing. The wire is fixed in a special mechanism that resembles strong metal vice jaws. One end of it is inserted into a device similar to a small press or crusher, where the steel casing is gradually squeezed and stretched into a cone shape. This way, the wire is essentially machined into a pointed tip. Imagine a pencil sharpened at one end, only it's not graphite but cold, shiny metal. This sharpened end then easily fits into the first opening of the drawing machine, a small metal die. To the touch, such a sharpened part becomes thin, like a shoelace, but remains elastic and strong. This is where the drawing process begins, which will turn the rough wire rod into a thin steel wire for the cable. Picture a shining metal strand, about the thickness of a pencil, being gradually pulled through a series of metal rings. Each of these rings is a drawing die, looking like a coin with a hole in the middle, but made of super hard material, like tungsten carbide. The holes in each die are slightly smaller than the previous ones. The whole system is arranged in a line, like beads on a thread. The wire passes through the first ring, and it compresses it, stretches it, reducing its diameter. Next, the following ring, even smaller, and the same thing happens again. The entire wire is pulled by a powerful drawing machine resembling giant toothed rollers or high traction rollers. It constantly pulls the wire forward, maintaining tension and thus forcing it to pass through the dies. To the touch, after several passes, the wire becomes thinner and longer, like a silvery strand of hair. The surface is smooth, cool, with a clear metallic sheen. Importantly, this entire process happens without heating. The metal remains cold. That's why it's called cold drawing. The steel gets stronger in the process. Its structure becomes denser and more durable, like a muscle that's been trained. And so, ring after ring, an ordinary wire rod transforms into a high-precision wire for a future steel cable. The steel thread that has just passed through a series of drawing dies has become thinner and stronger, but at the same time, stressed, like a stretched string, with fatigue hidden inside. The metal has accumulated internal stresses, microscopic defects that reduce its ability to bend or stretch further without cracking. Yes, this wire has become brittle. To release this stress, the wire passes through a special thermal furnace. It's not visible from the outside. It's a long metal tunnel structure, inside which the temperature reaches over 1,000 degrees Fahrenheit. In such heat, resembling the middle of a bonfire, the wire slowly moves through the furnace, either lying on moving rollers or suspended. It gradually heats up to the required temperature and then slowly cools down. The whole process takes anywhere from a few minutes to an hour, depending on the thickness and grade of the steel. To the touch, the wire after this stage is just as smooth and shiny, but it no longer breaks. Inside the metal, its crystalline structure has rearranged itself. The stresses are relieved, plasticity is restored. Now it's ready for the next series of drawings, and it will become even thinner, stronger, and more durable. It's like giving muscles time to recover before a new workout. In the final stage, the wire undergoes a final quality control, and this is definitely not a simple visual check. A long, almost continuous strand of shiny metal moves at a speed of tens of feet per second through the inspection unit. There, it's met by special sensors. This could be laser equipment that non-contact measures the wire's diameter with an accuracy of thousandths of an inch. Nearby, devices that determine strength. A portion of the batch is selected for mechanical testing. The wire is clamped in hydraulic jaws and pulled until it breaks. This determines its tensile strength and breaking load. If the wire holds up, it's ready for work at heights of hundreds of feet, supporting the weight of a car bridge. The surface is checked separately for microcracks, burrs, corrosion. High-resolution cameras or even eddy current testing are used here, which can see beneath the top layer of metal. And only the wire that has passed all these tests gets the green light. It will become part of a steel cable, capable of withstanding years of loads and harsh weather. This is the final touch that guarantees what arrives at the construction site is reliable, like steel itself. After inspection, the quality wire is neatly wound onto large spools. The wire passes through guide rollers and tensioning mechanisms that ensure the coils lie tightly, but not too tightly. All this happens on high-speed winding machines. Spools come in different sizes. For thin wire, they might weigh hundreds of pounds. For thicker wire, a ton or more. Then these spools head to the next stage, the actual twisting into cables. But even before this, they are sometimes coated with an anti-corrosive compound or lubricant so the wire isn't damaged during storage and transport. Spools of wire are usually moved using forklifts, cranes, or special carts because the weight of even one spool can reach several hundred pounds or more. Manual labor is ruled out here. Otherwise, the risk of injury would be too high.